All right, we're talking today about scalar products. There's actually two types of vector products. There's the scalar product of two vectors, which is one we're going to talk about today. And we generally represent that with a dot, and it's referred to as A dot B. And then there's the vector product of two vectors. The scalar product is called the scalar product because it results in a scalar, in other words, a number. The vector product results in a vector, and we call that one A cross B, and we use kind of the more traditional multiplication sign for that. So two different vector products. We're going to start today with the scalar product only. So let's define it now. The scalar product is more commonly known as the dot product, occasionally called the inner product, but generally we'll just refer to it as the dot product. And I've got it defined in 3 dimensions, but it works in any dimensions, 2 or 3. So if you have a vector that has components a1, a2, a3, and another vector b with components b1, b2, b3, the scalar product a dot b is defined as a1, b1 plus a2, b2 plus a3, b3. So what you're doing there is you're just multiplying corresponding components, a1 times b1, a2 times b2, a3 times b3, and adding them together. All right. And so this is a quick example here. If I wanted to do p dot q in the example given right here, p dot q would be 2 times -1 plus 3 times 0 plus -1 times 2. So -2 plus 0 minus 2, which is -4. So note that that dot product or scalar product comes out as a constant, or in vector speak, a scalar. Now in this example, they're also asking me to find the angle between P and Q. So I haven't actually defined that yet. That's coming up right next. So let's jump to that right now. So for the angle between vectors, we can define the angle between vectors as the dot product divided by the product of the magnitudes. So A dot B divided by the product of the magnitudes of the vectors A and B. So let's look at 2 vectors here. And probably for simplicity's sake, why don't we just make them 2-dimensional vectors? I don't think I really need, I don't know why I would choose to make them 3-dimensional vectors, because it works the same way. So let's just assume these are 2D vectors, okay? Well, in the diagram up above, if I connect the hypotenuse here, right there, I have a triangle, right? And the sides of this triangle have lengths given by the magnitude of the vector A, the magnitude of the vector B, and then let's consider what the third side is. If you took the vector A and you added it to, say, this unknown here, by vector addition, that would result in the vector B. So A plus X is the vector B. So let me back off here for a second. So if that's the case, then that implies that that third side is equivalent to the vector B minus A. So I'm going to call it that, vector B minus A. All right. And then let's consider the law of cosines. So we know the law of cosines tells me that if I take the magnitude of the vector B minus A, that's the length on the far side there, squared, that's equivalent to the magnitude of A squared plus the magnitude of B squared minus 2 magnitude A magnitude B cosine of the angle theta. So what I'm doing here is I'm applying the law of cosines to the triangle you see up above using the magnitudes. All right, well, if we define A to be A1, A2, and B to be B1, B2, then it follows that the vector B minus A is going to have components of B1 minus A1 and B2 minus A2. All right? So the magnitude of that vector on my left-hand side here is going to be B1 minus A1 quantity squared plus B2 minus A2 quantity squared, square root, but then I'm squaring it, which undoes the square root. Similarly, the magnitude of A quantity squared is going to be A1 squared plus A2 squared, and the magnitude of B quantity squared is going to be B1 squared plus B2 squared, minus 2 magnitude A, magnitude B, cosine theta. So I'm just going to expand out the left-hand side. Now I'm going to have B1 squared minus 2 A1 B1 plus A1 squared plus B2 squared minus 2 A2 B2 plus A2 squared is equal to A1 squared plus A2 squared plus B1 squared plus B2 squared minus 2 magnitude A, magnitude B, cosine of theta. And now we get some stuff to cancel out here. I got a B1 squared on this side and a B1 squared on this side. I got an A1 squared on this side and an A1 squared on this side. B2 squared, B2 squared, A2 squared, A2 squared. So what do I have now here? I have negative 2 A1 B1 plus A2 B2. So I just took these last two terms that were left on this side, factored out a negative 2. And I have that equal to a negative 2 magnitude A, magnitude B, cosine of theta. And now I'm going to divide both sides by negative 2 magnitude A, magnitude B. Negative 2 magnitude A, magnitude B. Result, cosine of theta, cross the negative 2's out. My denominator is the product of the magnitude of A and the magnitude of B. And my numerator, A1 B1 plus A2 B2, well, that is equivalent to A dot B. So I have my result. So this is an equation that comes in IB math quite often. It's the method by which we're going to find the angle between two vectors. We're going to take their dot product, and we're going to divide by the product of the magnitudes, and that will be equivalent to the cosine of the angle in between the vectors. And I adjusted this to 2D instead of 3D, but it applies equally well in 2 dimensions as it does in 3 dimensions.